AP Chemistries, this is Mrs. Vandal. Bringing you Chapter 11, Part 12. This is your crystalline solids, the fundamental types. So I know we skipped several sections. 11.8, we talked about the phase diagram. So if you're truly interested in knowing when you can liquefy carbon dioxide, check out section 11.8. 9, 10, and 11 talk about the way ionic crystals are formed. The AP Chemistry curriculum has said, oh, we don't need to cover that anymore, so I am skipping all of that, okay? If you are truly interested, go back and check it out. But what I would like you to do is go into your book, find your book, and go to page 526. And I like this graphic right here. I think it will help you as I talk about these 5 different kinds of solids, and use this as a reference as I'm going through them, okay? So if you need to pause this and find your book, then go ahead and do that. All right, so molecular solids, molecules. I'm thinking of covalent compounds, all right? So molecules are covalent. They're held together by the intermolecular forces. That could be either hydrogen bonding, dipole, or London dispersion. In general, they have low melting points. Some are higher than others. So some examples of these would be water, carbon dioxide, and even sucrose. Did you know that sucrose can melt with the heat of a candle? Yes, it can. Okay, so considering most of the solids that we're going to be talking about in this section, it does have low melting points. Even though I know sugar seems pretty high, it really isn't. Okay. Why? Because intermolecular forces are actually the hydrogen bonding, the dipole, and the London dispersion are going to be weaker than most, not all, most of these solids that we're talking about. Ionic solids are composed of ions, okay? Surprise, surprise. So some of the examples might be sodium chloride, calcium oxide, and cesium chloride. They have higher melting points, definitely much higher than the ones above, the molecules, the covalent molecules. Why is that? Well, cations and anion charges, these are a full positive and a full negative charge. These are stronger than your polar, than your partial positive and your partial negative charges, okay? And so I know we've referenced Coulomb's law before. And Coulomb's law says force is equal to a constant times Q1, Q2. Those are your charges divided by radius. I think it's just radius, not r squared. So kind of cross out that square part, okay? That really doesn't make any difference. The proportionality is what truly matters here. So what is the effect of charge? What happens if the charges increase? Well, guess what? The greater the charges, the greater the attraction. Here we go. So what does that mean? If you have a +1 and a -1 charge, it's going to have less attraction than a +2, -2. So if I scroll up here just a little bit, so if I have sodium chloride and calcium oxide, sodium is a +1, chlorine is a -1. Calcium is a +2, oxide is a -2. What does it tell me? That calcium oxide has greater attraction for each other than sodium chloride does. So what about the effect of radii? Well, look at this proportionality here. Radius is in the denominator. So if I have a small radius, what happens to this whole term? It gets bigger. So the smaller the radius, the greater the attraction. And so we haven't covered this yet. I know this is some of the stuff that we skipped in chapter 7 and 8, but as a rule, look up here, look at this. Here's a periodic table. So as I go to the upper right-hand corner, you're getting smaller. Why is that? Well, if I look down at francium, it has 7 shells, all right? Cesium has 6 shells, yada, yada, yada. So, hydrogen has 1 shell, lithium has 2 shells, sodium has 3 shells, potassium has 4 shells. So the more shells as you go down, the bigger the atom is, in this case, even the ion. And what if I go this direction? I'm getting smaller. That seems to be an opposite, people get confused over that. It doesn't seem to make sense. Well, it does, because as you go across a period, you have more protons, you have more attraction between the nucleus and the outer electrons, okay? We will talk much more detail about this towards the end of the year, but for right now, just understand as you go towards helium, helium is the smallest atom and francium is the largest, okay? All right, so which one has the greater melting point? sodium chloride or magnesium chloride. Well, what do they have in common? They both have chlorines, all right? So it's really a matter of sodium magnesium. So if I look at sodium magnesium over here, they're side by side. Their radius isn't that much different from one another, okay? So what does make a difference is their charge. So sodium is a +1 charge, magnesium has a +2 charge. That will actually take priority over the fact that they're in the same shell. Magnesium is slightly smaller. So it's the fact that magnesium has a +2 charge is what makes it have a greater attraction. And now which one is a greater melting point, sodium chloride or cesium chloride? This is a +1, this is a -1. This is a +1, this is a -1. So it's not the charge, it must be the radius. So which one do I want? I want the one that has the smaller radius, the greater attraction. So which is smaller, sodium at 3s1, 3 shells, or cesium at 6 shells? So which one's smaller? It is sodium. So it will have a higher melting point than cesium chloride, okay? And we will practice this, don't worry. So as we continue on, what have we accomplished? Let's kind of go back here. We have looked at molecular solids and we've looked at ionic solids. Hopefully you understand which is which. So now here is the third type broken down into 3 different groups. That's atomic solids, okay? So let's talk about the atomic solids. So just even look at what does that word even mean. Atomic solid means atoms, not molecules, but single atoms that are solids, all right? So if you look at the periodic table, it's divided into 2 main categories. We have the metals and the nonmetals. So we are seeing for the first time the non-bonding atomic solids. These are your nonmetals that are solids that have no other attractions besides the weak London dispersion. There's nothing holding one atom to the next. There is no partial charges until they come right next to each other, and that's how the London dispersion or the van der Waals forces work, all right? So we're talking about solid xenon and solid argon and solid neon, you know, things that you don't even think about as being solids. After all, aren't these called noble gases, all right? So what does it tell you about the melting point? These are incredibly low. You can also include like solid oxygen and solid fluorine and solid chlorine. And then if you look at the halogens, iodine is a solid, all right? So it is a solid at room temperature. And that's one of the few ones, the non-metals, that are solids at room temperature. But some of these other things, there's no way. I mean, I've never seen in my life solid xenon before. I'm not even on YouTube. I haven't looked it up, I guess. So those have extremely low melting points. By the way, iodine, which I referred to earlier, it does, I mean, it's a solid at room temperature, but it takes only a little bit of heat for it to also become actually a gas. It goes straight into the gas phase. Metallic solids, this is the rest of the periodic table. So what are we talking about? Things that you know that are metals. Let's say iron, gold, aluminum, those are metals that you're very aware of. And how do these work? These are held together by metallic bands, meaning what? Metal cations, the nucleus, surrounded by what is called the sea of electrons. So their valence electrons are all kind of shared by one another, creating a very stable condition here. And if it's that stable, it means it has a high melting point. Off the top of my head, gallium is the only metal I know that will melt in your hand. It's still a solid at room temperature, but it melts in your hand. As you know, mercury is a strange bird anyway. It's a liquid at room temperature. And other than that, most of your metallic solids will take a lot of energy to make a liquid out of it, okay? Like tungsten is used in the old filament light bulbs because it has such a high melting point, okay? And it's that sea of electrons that gives it that stability. That's what causes it to be a good conductor of electricity too while we're at it. All right, let's go to the next page. So this is the third type of atomic solid, or the 5th type overall. These are your network solids. These are atomic solids. So these are special cases of atoms and how they're bonded. And this really works mostly with carbon, okay? As you might think of, well, carbon has a very, very high melting point. Carbon in the sense of a diamond, or in graphite, or even in charcoal. All right, you rarely see melted charcoal, All right, you burn it instead. You don't melt it, do you? Okay, so what makes carbon so incredibly special? All right, it's this network covalent. And when I think of network, I think of like a spider web. I don't know why, or, working the web or, things like that, where everything is interconnected. And that's what's going on here in the diamond and here in the graphite. In the diamond's case, that each of them, the main carbons are tetrahedrally connected to all the other carbons, making it incredibly strong, okay? As you know, diamonds are very, very strong. They're used for grinding things, all right? Well, the hardest substances on Earth. Over here is your graphite. If you look at it, especially look at like this one right here. Do you see this carbon right here? If you look at it, it is trigonal planar. And if it's trigonal planar, if you remember your hybridization chapter from chapter 10, that means it's sp2. Well, wait a minute, I thought carbon, sp2, where's that other bond? All right, well, it's this vertical right here holding the next layer together. And that's what makes graphite so special. We use graphite and pencil, so every time you write, you are smearing one layer of those carbon atoms across from the second layer, et cetera, et cetera. It's also used as a lubricant, okay? So let's see what we say down here, okay? So diamonds, there's a large gap in energy between these occupied and unoccupied orbitals, makes diamonds a very poor conductor of electricity. It means it doesn't, it's an insulator. It consists of these carbon atoms all bonded tetrahedrally, like I already said. It's sp3 hybridized and 109.5 bond angles, all right? Making it very, very special. These are all carbon atoms. Graphite, if you look at this, I've kind of already explained all this already, so you can read it, blah, blah, blah. sp2, trigonal planar, and these weak bonds right here is what makes it a lubricant, which makes it good for graphite, okay? Let's go to the next page. And the third one that's network covalent, we're kind of cheating here with the definition. We're going to talk about silicon, which is the element right below carbon, but it's not pure silicon. It's silicon dioxide, which is your quartz, which is what sand is made out of. So you all understand what sand is. And when you work with the sand, you kind of melt it, you can produce glass, okay? And so, again, very, very similar to diamonds, where it's that tetrahedral arrangement with the silicon and the oxygens. And so we consider this also a network covalent with an extremely high melting point. And here in your notes is a way to, again, look at these 5 different types. This came from the Zumdahl book. I like the one out of your Tro book really well too. So if you want to look at this as a reference, you can, or look at your book. And what I would like you to do now is problem set number 21. I want you to pause this. Think about what I said, look at either your book or look at this chart right here and try to classify each of these in problem set 21 as its type of solid. You only got 5 choices, all right? So once again, it's either a molecular solid, ionic solid, the non-bonding atomic solid, the metallic, or the network covalent. So go ahead and do problem 21, and when you are done, come back. So gold is a metal, hopefully you knew that. Dry ice, CO2, molecular solid. Lithium fluoride, metal, non-metal, ionic. Krypton is normally a gas, it's a noble gas. It's a non-bonding atomic solid. Quartz is your silicon dioxide, network covalent, like I just explained right above on this page. SF2, it's not an atomic, is it? So it's either a molecular solid or ionic solid, so it's not ionic, must be molecular. Copper is a metallic. The sucrose is, again, a molecular solid. Why? How do I know that? It's not an atom, is it? So it's either a molecular solid or an ionic solid, and it ain't ionic, so it must be molecular. Xenon is a non-bonding atomic solid, and diamond is network covalent. So what I would like you to do next is, to be honest, I want you, when you're done, Google, yes, Google, I mean, I'm giving you permission to use your phone here, and look up the melting points of each of these, okay? So you probably start recognizing this as a network covalent, as a non-bonding atomic, ionic, metallic, molecular, all right? And then let's see if we can rank and base kind of these ideas on your findings. So we're going to talk about this first thing next time. Well, I'm out of time. This is the end of chapter 11. Woohoo! Okay, so don't wait to be great. See you next time. Bye-bye.